Hey everyone, this is lecture 23 about magnetic flux, Faradays law and Lenz's law, and understanding these laws are main goals in this lecture. First, I will quickly talk about magnetic flux. It's simply how many magnetic field lines passes through a loop. It could be a square loop, rectangular, like you see in this picture, or square, circular, doesn't matter. We learned about how magnetic field lines can be mapped, and if they are close we have larger magnetic field and so on. Assume these are magnetic field lines. I have a loop in front of them, and how many of those are passing through my loop is the magnetic flux. Simply, it's similar to air flux. If I ran this fan and put my rectangular loop here, there will be some part of it passing through the loop, and we can all realize that if we rotate the loop, as the loop rotates, the amount of air passing through it will change. So change in angle will change the magnetic flux or air flux. Here is the loops shown from the side. These are magnetic field lines passing through it. If I tilt it, I can clearly see that some lines are not passing through it anymore. Some are left, but the flux definitely decreased. So that's magnetic flux. How do we calculate it? Is the simple equation here. It's the effective area times the magnetic field. Effective area would be area through which some magnetic fields are passing. So that will be the area times the cosine of the angle between the normal of the area or axis of the area and magnetic field. Here in this figure we can nicely see what these are. This is my loop, again edge weave. Assume we have, going into the board, we have a rectangular loop. This is the normal or axis of the loop. And angle between the loop and the magnetic field, the aqua lines here are magnetic field, and theta is the angle between the loop and magnetic field. This also would be my theta here. And that's how we calculate the magnetic flux. Unit of it is Tesla times the meter squared. Magnetic field unit is Tesla, of course, and area in SI unit would be meter squared, and there is a special name for it called Weber. Here we see different images showing different cases of fluxes, angles, and so on. I have a circular loop here. Magnetic field is upward. Some lines are passing through my loop, and here is the normal or axis of the loop. And I can calculate the flux using this equation. These three sequence of figures are shown here where I can have a maximum flux when my normal or axis is parallel to magnetic field. Then cosine theta is 1, which is the maximum value cosine I can have. Then we have the maximum. We have minimum if normal is perpendicular to the magnetic field. Then we'll have cosine theta 0. Or I can see in the figure here that no magnetic field lines can pass through my area because they are passing either under or over, because my area is parallel to magnetic field. My magnetic field lines should be piercing through the area if I have a flux. And in this one here I have a tilted loop, and I have my flux as VA cosine theta, either maximum or minimum. The side figure here is showing if I have one loop, I have a flux. As I always calculate, I calculate phi as VA cosine theta, like in the equation you see on the upper left corner. And if I have more than one loops, what I do is I multiply my flux by the number of loops. So flux for one loop would be that up here. Flux for n loop would be n times flux for one loop, right? So it will be NBA cosine alpha, cosine theta. That's flux. And if that flux is changing, we have a change in flux, we have an induced magnetic field. Over here I have only magnetic field lines shown. They're out of the board, and we can easily see if we draw a rectangular loop, for example. Let's say this many numbers were passing through it, and if I tilt my rectangular loop, let me try to draw that. In a direction, I will see that less magnetic field lines are passing through it. Alright. This is a quick check question here. Which loop has more flux passing through it? You can literally count the number of magnetic field lines passing through. 4 here, 6 here. Of course, larger loop will have more magnetic field lines passing through them if they have the same angle with the magnetic field, which is the case here. So loop B is the answer here. This question is giving us a loop of wire with area A is tipped at an angle theta, as you see in this figure here, to a uniform magnetic field B. This is our magnetic field. The maximum flux occurs at angle 0, as we know, right? Phi maximum is B times A times cosine theta. If theta is 0, then cosine theta is 1. This whole thing becomes 1. Then we have B times A, and that's the maximum flux. Max flux. What angle theta give a flux that is 1/2 of this maximum value? So we calculate that flux, BA cosine theta, and that should be equal to the maximum flux over 2. And we said maximum flux is BA. We put that in here. We'll have B times A times cosine theta equals B times A over 2. And then we will find our cosine theta. Cosine theta is equal to 1/2. Then our theta is equal to cosine to minus 1/2. And if you carry out this calculation, you'll find that the angle is 60 degrees. So C is the answer here. The metal loop is being pulled through a uniform magnetic field. Is the magnetic flux through the loop is changing? So B is not changing. B is uniform. Assume that the frame is not going out of the magnetic field region. So we assume this region of magnetic field continues forever. So this loop is never going out. As I pull it to the right, the number of magnetic field lines passing through the loop will not change unless it's going out of the magnetic field, and the question says it's not going out of the magnetic field region. So is the flux changing? No. If I rotate the loop though inside the magnetic field, the angle theta will change, so flux will change. Theta changes, so flux changes. This question here is a nice calculation of a flux. We have a circular loop here, and we have magnetic field of the earth going towards the right, tilted 30 degrees from the normal. In the question we are given the 60-degree angle, so we have to be careful about this. We have to find the angle between the magnetic field and the normal or axis of the surface. Normal or axis. And the question is asking us what is the magnetic flux through this loop. And here's our equation, AB cosine theta. We found our theta and we will just apply that. The area would be pi r squared because we have a circular loop. This loop is coming out here, going back in, and it's a circular loop. That's about this question. Now, if there's a flux change, there will be an induced current and induced magnetic field. That's an idea we learned. Now, how will the direction of this induced current and magnetic field will be defined is by Lenz's law. Lenz's law says that there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in the flux. So what we are going to do is we're going to look at what is happening to the flux through my loop. Over here, the picture we have is we have a magnet and it's moving down. This is the direction of motion. And as it is moving down, the magnetic field of this magnet is north to south, right? So they will always originate away from north, go through this loop down, and then turn back to south. This part we're not interested in, but here the background magnetic field is down. That's what we're interested in. B is down, and as my magnet comes closer, B increases, so B induced will be in the opposite direction to stop that increase. So we'll find this guy first using that idea, the Lenz's law. If magnetic flux through a loop is increasing, the loop will generate an induced magnetic field against the background magnetic field to stop that increase. We'll find that first. It will be in opposite direction, of course, the background magnetic field. And then we'll use right hand rule 2, shown in here. Roll your fingers along the current, your thumb along B, magnetic field, and you have the direction of current and magnetic field here. Current and magnetic field is up, the direction of thumb. In the case of applying Lenz's law, we have magnetic field up, so I'm gonna put my thumb up first. Right, let me show it right over here. My thumb should be up, and then I should roll my fingers, right? And my fingers roll in direction will give me the induced current. So this is B induced. This is exactly what we see in the picture actually, and this is I induced. It's already shown in here, but we wanted to go over it to understand what is there. Alright, similar ideas here. First one is the one we have magnetic field, magnet stationary, magnetic field is constant, not changing, no induced current, no induced magnetic field. If there is no flux change, induced current and induced magnetic field do not exist. But if it's coming closer, as we considered in the previous page, it will generate a magnetic field inverse to the background magnetic field. The background magnetic field is down, B induced will be up, and second right hand rule tells us that the current, induced current, should be in this direction. Looking from the top, that would be counterclockwise. If I move magnet away, this is the motion here now. If I move magnet away, background magnetic field is down and decreasing. You see those lines are all background magnetic field lines. Now B, down and decreasing. My B induced will be in the same direction to stop the decrease, right? It doesn't like any changes because flux is changing. Decreasing, it will try to stop that and generate an induced magnetic field downward to do that stopping, and that will be due to an induced current, which should be clockwise, looking from top. That's Lenz's law. And this page summarizes Lenz's law and what we should do. What we should do is first look at what is happening, and then decide the direction of induced magnetic field. Then use right hand rule 2 to decide the direction of induced current. That's the steps we're going to take. One example here, the bar magnet is pushed toward the center of wire loop, which is true. There's a clockwise current, counterclockwise current, and no current induced. I'm pushing this upward. Its background magnetic field is also upward. I'm going to draw that with blue. That was my theme here. Background magnetic field is blue. So flux upward is increasing. Again, it's from north to south. It comes back, but we're interested in the part where they go into the flux, right? So B, background B, upward and increasing. What's going to happen to my induced magnetic field? It will be downward. B induced will be down, right? Because it wants to stop that increase. And if I put my thumb down, it will be this situation here, right? Thumb down. Hard to draw, hard to draw. Roll your fingers. It will be something like that. So you'll have B induced down and I induced in that direction. I should have put it up there in this direction, right? I induced here, just like that. So we have, looking from the top, clockwise, right? So there will be a clockwise induced current. And here's the answer. The bar magnet is pushed toward the center of the wire loop, which is true. In this case, magnetic field lines are parallel. Nothing is passing through my loop. There's no flux to begin with. No flux change, no current. That's what we say. No flux change, no induced current. All right. This question here, more subtle and it's gonna take time. I'm gonna put another video slowly discussing it. My video is getting long already, so I'm gonna skip this. Answers are here. Go through and try to freeze the video and try to see why are the answers, but I'm gonna put a separate video for this question. Another quick check here. A magnetic field goes through a loop of wire as shown at right. If the magnitude of the field is increasing, decreasing, constant, what can we say about the current in the loop? Similar. I'm going to go through this as well, but the answers are here. Very similar idea. Look at what is happening to flux. If the flux is increasing, my induced magnetic field is against the background magnetic field. If the flux is decreasing, my induced magnetic field is in the same direction as the background magnetic field. And try to convince yourself that these are the answers, but I'm gonna put another video on this. Alright, this question here, I'm pulling this guy out of the magnetic field here. What is the direction of current? Flux is inward and decreasing because magnetic field, background magnetic field is inward and decreasing. Flux is inward and decreasing. I'll just show B. B is the background magnetic field decreasing. So induced magnetic field will be the same direction as the background magnetic field into the board. This is my B induced. Then using right hand rule 2 for an into the board magnetic field, this will be my current. Please try the right hand rule too and convince yourself that that is my current. It's very hard to draw a thumb into the board. If thumb is into the board, the 4 fingers will roll in this direction. Alright, something like that. So which direction is that? Clockwise. Clockwise. This one is a bit more involving. I'm moving this loop close to a current carrying wire. What is happening? What is the direction of current? Is there a current? First, I'm going to use first right hand rule to find the direction of magnetic field of this current at these areas, right? And if I apply it, my thumb should be to the right, and then I roll my fingers, and this will be my rolling fingers direction. So up there I have my fingers going into the board. Down here will be out of the board, but I'm interested in up there, right? There's an into the board background magnetic field. I'm going to use blue again for the background magnetic field. So here's my background magnetic field. As my loop is coming towards the wire, I know if I get closer to the wire, B will increase. So background magnetic field into the board is increasing inside my loop. This background magnetic field is everywhere, by the way, not only here, it's all everywhere, right? And as we go farther away, it decreases with the distance. So here too, so there is a flux going through my loop. Initially magnetic field was smaller. As it gets closer to the wire, magnetic field increases, background magnetic field increases, and my loop will not like that. It will generate a background magnetic field, induce a background magnetic field in the same direction. It becomes almost the same question then. Into the board, background induced magnetic field, this will be the induced current direction. There will be a clockwise current. This quick question is about how the amount of induced current is related to the motion of the object, or the change, how fast the flux is changing. So the question says a long conducting current carrying wire runs next to a loop of wire, as you see in the figure. The current in the wire varies as shown in the graph. This time actually I just put this figure here for symbolizing, but we're not moving the loop closer. This time current is changing in the wire. If the current is changing, magnetic field of the wire will be changing. Current increase in magnetic field will increase, current decrease in magnetic field will decrease. We can put the equation here if you like, we don't really need, but directly proportional to current. And this will cause a flux change. So if current increases, B increases, and if B increases, flux increases, right? More flux through this guy, and that will cause an induced current. The question is asking us not the direction, but which segment will induce the largest current. The quickest change will induce the largest current. If you look at here, there is a change, but it's happening slowly. Here too, no change in the C segment. There's some change, but none of those is as quick as the drastic drop of current here. Current drastically drops, and phi will also drastically drop because magnetic field will drastically drop. So quick change causes quick, larger induced current. I'm also going to leave this for a video solution, and I want to move to Lenz's law now, Faraday's law now. Faraday's law becomes a simple matter after we understand Lenz's law and find the direction. We can find the induced EMF, electromotive force, or you can assume this as a potential difference, although it's not exactly potential difference. We will find this value of this by change in flux divided by change in time. So I'm going to look at how much flux changed and how much time it took to change. Flux unit was Weber or Tesla meter squared second, and the unit of epsilon EMF will be volt as always. If I have one coil, that's what I have. If I have more than one coil, n coil, that's the equation I am looking at. So what we will do, our steps will be to define the direction of induced current and induced EMF, induced current and induced magnetic field using Lenz's law. First, we define the direction of induced magnetic field, use right-hand rule to define the direction of induced current, and then calculate the induced EMF using Faraday's law. Then we can calculate current and so on using Ohm's law. This page here is showing how many different types we can change the flux. I can put my magnet closer to my loop, flux changes, or farther away, flux changes. I can change the area of my loop. I stretch my loop here, area decreases, flux decreases inside it. Or I can push by my bar here. I have a loop here. This is a square loop. I can push my bar to the right or left. The loop area changes, flux changes. And I can rotate my area inside the magnetic field, flux changes. Whenever flux changes, there is induced magnetic field, induced current. How do I calculate induced current? I get my epsilon induced EMF from Faraday's law, and induced current can be calculated using Ohm's law. And we find the directions always using Lenz's law. So Faraday's law allows us to find the magnitude of the induced EMF and current, and Lenz's law allows us to determine the direction. This page summarizes everything. I'm looking for an example here. Alright, let's look at this example. A patient having an MRI scan has neglected to remove a copper bracelet. The bracelet is 6 centimeters and has a resistance of 0.01 ohms. So a patient here and has a bracelet, forgot to remove a bracelet, so there will be a flux through that. Alright, and the bracelet has 6 centimeters diameter. Let's put it in here, 6 centimeters. And I'm gonna go the radius directly. We're gonna need that area for flux probably. So 3 centimeters is the area of the bracelet, right? Alright, let's keep reading now. The magnetic field in the MRI solenoid is directed along the person's body from head to toe, head to foot. Her bracelet is perpendicular to this magnetic field. So there is a magnetic field passing through the bracelet, head to toe, head to feet, and head to toe. So there's a flux, right? These yellow lines are magnetic field, and there's a flux. Alright. As the scan is taken, the magnetic field in the solenoid decreases from 1 Tesla to 0.4 Tesla. So we have a B initial, 1 Tesla, and B final. 0.4 Tesla in 1.2 seconds. So the total time passed while that decrease is happening in 1.2 seconds. What are the magnitude and the direction of the current induced in the bracelet? I induced, question mark, direction and magnitude. I'm going to try to draw this loop, this bracelet here larger. Oh, that's a terrible drawing. Okay, try again. Alright, this one is better. Magnetic field lines are passing through it. Let's show several magnetic field lines piercing through it. So it has a flux. And that magnetic field, what's happening to it? It's decreasing, right? It's decreasing. So if this magnetic field is decreasing, my loop will generate a magnetic field in the same direction. So B induced is also to the right. Using right hand rule, keeping my finger thumb to the B induced and curling my fingers along, I will have this type of curling. I induced. I know this is a terrible drawing, but I think it does an okay job in showing the directions and right hand rule. Now this is my I induced. Alright, that's the direction. We'll come down here, go back into the board. Alright. Maybe too many I induced lines. I'll just leave it like that. Now let's find that I induced. What we do is to find epsilon induced first. It will be n times delta phi over delta t, and then use that to find I induced, which is equal to epsilon induced over r. Now they should be giving us a resistance of that bracelet. So it's along this bracelet there's a resistance. We can assume there's a resistor here. It has an R, and that R is given to us. R is 0.01 ohms. Here N is 1, and delta phi over delta t we'll find from using these. So first, we find the flux and how much it changes. To find the flux, here is our equation. A, B, cosine theta. Theta is 0, so this guy is 1. Because if I look at my loop is here. Normal to my loop is parallel to the magnetic field. Maybe I'll show it as a green line. In this direction would be more clear. That's normal or axis of my loop. Alright, so from there we'll find the flux, but the flux is changing. We're gonna find delta phi. That will be phi final minus phi initial, and that will be A times B final minus A times B initial. I can take A parenthesis here, then I'll have B final minus B initial, right, times A, and that would give me my flux. An area, of course, pi r squared, we find that inserted in here, we will find our flux. I will quickly give you that value, and so it should be about 0.0017 Tesla meter squared or Weber. That's our flux. Now inserting that flux here, n is 1, will have 0.0017 Weber over the time, which is 1.2 seconds, right? Given here, or we wrote it down there, 1.2 seconds. That will give us an induced EMF of 0.0014 volts, or that's 1.4 millivolts. Input that in here. For the current, you should find as 0.14 amperes. Alright, that's a question, very nice question, where we both use the Lenz's law, right, to find the current direction, and Faraday's law to find the value of induced EMF, and finally Ohm's law to find the induced current. Alright, that's it. I'll see you in the next lecture.